Hello there, and welcome back to the Sleep Science. Tonight, you're standing beneath a star that looks perfectly ordinary. The sun hangs in the sky with its usual blinding confidence, pouring golden light across rooftops, oceans, and the top of your head. It feels steady, reliable, like it'd been doing the same dependable job for 4.6 billion years, without so much as a sick day. But high above you, far beyond blue sky and drifting clouds, something subtle has just happened. A pulse, a ripple, a strange flicker of energy that left the sun and began racing toward Earth in a way we've never quite seen before. You don't notice it at first, of course. You're busy being a human. Maybe you're scrolling. Maybe you're reheating coffee that you forgot about 10 minutes ago. Meanwhile, photons, tiny packets of light, are already halfway across the void. They left the solar surface at 300,000 kilometers per second, crossing 150 million kilometers of space in roughly 8 minutes. That's the mainstream fact you probably learned in school. Sunlight takes about 8 minutes and 20 seconds to reach Earth. If the sun blinked out, you'd still be blissfully unaware for those 8 minutes, which is comforting and slightly terrifying. But this pulse is different. It isn't just visible light. It's a complex surge of energy, radiation, and charged particles braided together like invisible threads. Solar physicists will later describe it as an unusual configuration of electromagnetic emission layered with a rapid magnetic disturbance. At first, the sun looks calm through ordinary telescopes. Its surface still roils with convection cells the size of continents. Sunspots still freckle its face, dark, cooler regions caused by tangled magnetic fields. All very normal, suspiciously normal. Historically, we've cataloged solar flares and coronal mass ejections for decades. Since the space age began in the mid-20th century, satellites like SOHO and the Solar Dynamics Observatory have watched the sun constantly, measuring ultraviolet radiation, X-rays, and streams of solar wind. We've seen powerful eruptions before, giant arcs of plasma looping tens of thousands of kilometers high. We watch coronal mass ejections fling billions of tons of charged particles into space. So when scientists say this arrival feels unprecedented, they don't mean we saw something shiny. They mean the data doesn't line up with familiar categories. Imagine instruments quietly humming in orbit, detectors tuned to specific wavelengths, magnetometers listening for tiny shifts in invisible fields. And then just slightly, the readings change. Not enough to cause panic, not enough to trigger alarms, just enough to make someone lean closer to a monitor and squint. You might picture a dramatic Hollywood solar explosion, but reality is softer, stranger. The pulse that left the sun appears to combine frequencies in a pattern researchers haven't cataloged before. It's as if the sun briefly played a chord instead of a single note, a cosmic piano key pressed with unusual force. Historians still argue whether ancient observers could have noticed subtle solar variations without instruments, but today's scientists rely on spectral analysis, so precise it can detect minute shifts in ultraviolet intensity. Out in space, the pulse moves through the solar wind, a constant stream of charged particles flowing outward from the corona at hundreds of kilometers per second. The solar wind itself was first confirmed in the 1950s by physicist Eugene Parker, who proposed that the sun continuously sheds plasma. At the time, many doubted him. Now we name spacecraft after him. Science can be like that. First they frown at you, then they build a satellite in your honor. As the energy wave approaches Earth, it interacts with the heliosphere, the vast bubble carved out by the solar wind that surrounds our entire solar system. This bubble shields us from some interstellar radiation, like a protective cosmic umbrella. A slightly leaky umbrella, but still appreciated. And here's where things get quietly dramatic. The configuration of this incoming energy suggests a rapid magnetic reorientation embedded within the radiation itself. Not just particles, not just light, but a synchronized fluctuation in magnetic field strength. That's rare. Magnetic fields are invisible architects. They shape auroras, disrupt radio signals, and protect our atmosphere from being stripped away. When they fluctuate in unusual patterns, scientists pay attention. There's also a quirky tidbit whispered in certain corners of solar research. A small but persistent group of theorists once proposed that the sun may experience microscale magnetic hiccups, tiny reorganizations of its magnetic lattice that don't qualify as full flares. Most of these ideas never gained mainstream traction. Yet tonight's pulse carries a faint resemblance to what those fringe papers speculated about decades ago. Not proof, just an echo. Down here on Earth you feel nothing. No warmth beyond the usual sunlight. No dramatic flash. That's the thing about cosmic events. They're often profoundly indifferent to your immediate comfort. You probably won't survive a direct hit from a massive solar flare, without technological chaos. But this isn't that. This is subtler, a whisper rather than a shout. Deep in Antarctica, a research station's instruments record a slight uptick in high-frequency radiation. In orbit, a satellite auto-calibrates after detecting a momentary anomaly. Somewhere, a graduate student refreshes a graph and mutters, "That's odd." The sun itself rotates slowly, about once every 27 days at its equator. Its surface churns at roughly 5,500 degrees Celsius, while its core burns at around 15 million degrees through nuclear fusion, converting hydrogen into helium and releasing staggering amount of energy every second. 4 million tons of mass become energy each second via E equals mc squared. And yet, for all that violence, it usually behaves within predictable boundaries. Tonight, those boundaries blur just slightly. You stand beneath a sky that seems unchanged, unaware that 8 minutes ago a star rearranged itself in a small but meaningful way. The pulse is here now. It brushes the upper atmosphere. It tangles gently with Earth's magnetic field. Instruments listen. Scientists lean forward. And you, comfortably horizontal, are about to follow that energy back across space, tracing its journey from blazing surface to quiet arrival, because this is only the beginning of the story. The energy is already here, slipping into Earth's upper atmosphere with the quiet confidence of something that has crossed 150 million kilometers without stopping for directions. You imagine it leaving the sun just 8 minutes ago, because that's all it takes. Light, traveling at roughly 299,792 kilometers per second, covers a gulf between star and planet in about 8 minutes and 20 seconds. That's the mainstream number. It's so fast that by the time you notice sunlight warming your face, it's already ancient news. But the pulse you're following isn't just a beam of visible light. It's layered, ultraviolet radiation, X-rays, and a structured ripple in magnetic intensity braided together like invisible silk threads. As it travels, it doesn't move through empty nothingness. Space isn't empty. It's a thin soup of charged particles, magnetic fields, and faint dust. The region between the sun and Earth is shaped by the solar wind, a continuous outward stream of plasma first theorized by Eugene Parker in 1958. At the time, many scientists resisted the idea that the sun constantly sheds material. Now we have the Parker Solar Probe diving closer to the sun than any spacecraft in history, confirming that yes, the sun is basically a glowing fountain. As a strange pulse moves outward, it rides atop that fountain. Normally, sunlight spreads evenly, diffusing across space in predictable wavelengths. But this time, the energy carries a modulation, an oscillation in electromagnetic intensity that instruments later describe as phase-locked. That means multiple frequencies rose and fell together in synchrony, almost like harmonized singers hitting the same crescendo. Solar radiation doesn't usually coordinate itself so neatly. You drift with it in imagination. The sun shrinks behind you from a blinding disk to a bright coin. Around you, the heliosphere stretches vast and protective, a bubble inflated by solar wind pressure. It shields the planets from a significant portion of galactic cosmic rays. Without it, Earth's surface radiation levels would be dramatically higher. Life might still exist, but it would look very different, possibly glow-in-the-dark different, which sounds fun until you realize sunscreen will become a lifestyle. Halfway across, the pulse passes orbiting satellites, some monitoring Earth's weather, others peering into deep space. They don't react yet. The energy isn't interacting strongly with them. It's simply moving through. But subtle detectors register an unusual polarization shift. Polarization describes the orientation of light waves. Normally, solar radiation arrives with expected polarization patterns based on magnetic field alignment at the solar surface. This pulse carries a deviation, small, measurable, statistically stubborn. Historians still argue whether subtle changes in solar polarization could have influenced early climate shifts in Earth's past. It's an open debate, tangled in ice core samples and tree ring carbon isotopes. We do know that spikes in carbon-14 levels in tree rings have corresponded to past solar activity events, such as the Miyake events discovered in 2012. Those were massive cosmic radiation spikes recorded in ancient wood, likely triggered by extreme solar outbursts over 1,000 years ago. Tonight's pulse is nowhere near that magnitude, but it's unusual in its structure. As it nears Earth, the planet's magnetosphere comes into view, a teardrop-shaped magnetic shield generated by molten iron circulating in Earth's outer core. This geomagnetic field has existed for at least 3.5 billion years. Without it, solar wind would gradually erode the atmosphere, as likely happened to Mars. You can thank the churning metal 3,000 kilometers beneath your feet for keeping your air where it belongs. It's the ultimate invisible bodyguard. When the pulse meets this magnetic shield, something delicate happens. Charged particles spiral along magnetic field lines toward the poles. That's normal behavior. But embedded within the radiation is that synchronized magnetic ripple. When it encounters Earth's own magnetic field, there's a brief resonance, like two tuning forks humming in proximity. It doesn't shatter anything. It doesn't spark global blackouts. It simply amplifies certain frequencies within the magnetosphere for a fraction of a second. Up in low Earth orbit, a satellite's magnetometer records a tiny oscillation that doesn't match standard solar wind fluctuations. It's not strong. It's precise. Engineers will later replay the data repeatedly, convinced at first it's instrumentation error. Because when something new appears, the safest assumption is that you've messed up. Science is cautious like that. First, suspect yourself, then suspect the universe. Meanwhile, sunlight continues pouring down as usual. The visible spectrum remains unchanged to your eyes. Blue sky scatters through Rayleigh scattering, the shorter wavelengths bouncing off atmospheric molecules more efficiently than red ones. That's why sunsets glow crimson when sunlight travels through more atmosphere at an angle. All very familiar, all very comforting. But in the ionosphere, the charged upper layer of the atmosphere starting about 60 kilometers up, things stir. The ionosphere reacts strongly to ultraviolet and X-ray radiation. During solar flares, it can become more ionized, disrupting radio communications. In 1967, a powerful solar flare even caused the U.S. military to briefly suspect a Soviet jamming attempt before realizing the sun was responsible. Imagine almost starting an international incident because your star sneezed. Tonight's ionospheric reaction is subtler. A thin band of enhanced ionization forms at mid-latitudes, not just near the poles where auroras usually dance. It's faint, temporary, but it aligns suspiciously well with the arrival time of the pulse. There's also a fringe theory resurfacing in quiet academic corners that certain solar emissions might carry quasi-periodic magnetic packets capable of momentarily synchronizing with planetary magnetic oscillations. Most researchers treat the idea cautiously. The math is complex, the evidence sparse, yet the pattern tonight nudges curiosity awake. You lie there, perhaps unaware that your GPS signal traveled through this slightly perturbed ionosphere. It still works. Your phone still finds satellites. No drama, just a faint whisper in the electromagnetic environment. And that's what makes this journey fascinating. The sun's energy didn't roar. It arrived like a coded message, structured, synchronized, and subtly resonant. Not destructive, not harmless either. Simply different. The pulse completes its 8-minute voyage and dissolves into Earth's atmospheric systems, leaving behind data points like breadcrumbs. Somewhere, researchers begin connecting dots. Somewhere else, someone jokes that the sun just updated its software. And you, still beneath that seemingly ordinary sky, are about to see what happens when the instruments start whispering back. The whisper begins in orbit, high above you, where Earth curves in slow blue silence. Satellites glide through darkness at nearly 28,000 kilometers per hour. They are built to endure temperature swings from blistering sunlight to deep space cold within minutes. They carry spectrometers, magnetometers, particle detectors, quiet electronic senses extended into the void. Most days, the data they collect flows steadily and predictably, like a calm heartbeat. Then the rhythm stutters, not dramatically. No flashing red warnings, just a deviation, small enough that automated systems nearly smooth it out. A slight synchronization between ultraviolet intensity spikes and a micro-oscillation in the surrounding magnetic field. The Solar Dynamics Observatory, which has been watching the sun continuously since 2010, records a brief anomaly in extreme ultraviolet wavelengths. At almost the same time, a separate satellite monitoring Earth's magnetosphere notes a fractional but precise tremor. Individually, these readings mean little. Together, they form a pattern. You imagine a control room somewhere, dim lighting, multiple monitors glowing in cool blues and greens. A scientist leans back in their chair, replaying a graph. The sun's emission curve rises, falls, and then, that subtle harmonic ripple again. It's like hearing a faint overtone in a familiar song. You don't notice it the first time, but once you do, you can't unhear it. Mainstream solar science has long categorized flares by intensity, A, B, C, M, and X class, with X being the most powerful. This pulse doesn't fit neatly into any of them. It lacks the explosive X-ray spike of an X-class flare. It doesn't eject a massive coronal mass like the famous events that sometimes buffet Earth. Instead, it carries coherence, multiple bands of radiation rising and falling in lockstep. Historians still argue whether earlier space-era instruments might have missed subtle multiband solar events due to lower resolution. In the 1970s, detectors were far less sensitive than today's. It's possible similar pulses occurred unnoticed. Or perhaps this truly is new behavior emerging as the sun moves through an 11-year solar cycle. Ah, yes, the solar cycle. That steady, approximately 11-year rhythm in which sunspot numbers rise and fall, magnetic poles flip, and solar activity waxes and wanes. Discovered in the 19th century by astronomer Samuel Heinrich Schwabe, who spent 17 years patiently counting sunspots, it remains one of the clearest examples of stellar periodicity. Right now, the sun is approaching a solar maximum, a time of heightened magnetic chaos. More flares, more sunspots, more opportunity for strange surprises. Back in orbit, the Parker Solar Probe, launched in 2018, has been dipping to the sun's outer corona, sampling solar wind directly. It recently confirmed that the corona is far hotter than the surface below it, reaching temperatures of over 1,000,000 degrees Celsius. That's counterintuitive. Imagine standing near a bonfire and discovering the air 10 feet above it is hotter than the flames themselves. Physicists are still debating why the corona is so superheated. Magnetic reconnection is the leading explanation, but details remain elusive. Now, as researchers compare Parker probe data with Earth-orbiting satellite readings, they notice something curious. Minutes before the pulse left the sun, the probe recorded a localized magnetic fold, a sudden kink in the solar magnetic field, sometimes nicknamed as switchback. Switchbacks have been observed before, but this one displayed an unusually clean geometry, like a perfectly tied knot. Coincidence? Possibly, but scientists are professionally allergic to coincidence. You picture them aligning timestamps across multiple spacecraft. Solar observation isn't done from a single vantage point. We have satellites positioned at Lagrange points, gravitationally stable spots in space, like the L1 point between Earth and the Sun. From there, spacecraft such as SOHO maintain constant solar watch. The pulse passed L1 instruments 8 minutes before Earth's atmosphere felt it. The readings match. There's also a quirky footnote circulating in internal discussions. Decades ago, a small subset of researchers suggested that under certain magnetic stresses, the sun's plasma might briefly enter a semi-coherent oscillation mode, almost like a star-sized bell ringing. The idea was largely theoretical and difficult to test. Most papers on the topic gathered digital dust. Yet tonight's harmonic radiation pattern resembles, very faintly, the mathematical predictions from those old models. No one is claiming the sun rang like a gong. Let's stay calm. But the synchronization is intriguing. Meanwhile, on Earth, ground-based observatories join the quiet conversation. Radio telescopes detect a slight, broadband enhancement in solar radio flux. Not disruptive. Just tidy. Too tidy. It's the neatness that stands out. Solar events are usually messy, turbulent, chaotic. This one has rhythm. In Alaska and northern Canada, magnetometers embedded in the ground record tiny geomagnetic pulsations called PC1 waves, naturally occurring magnetic oscillations in the magnetosphere. They happen often. But tonight, their frequency briefly aligns with the incoming solar modulation, two systems humming in temporary resonance. If this were a dramatic disaster movie, alarms would blare. Instead, scientists sip cooling coffee and say things like, "That's interesting," which in research language is the equivalent of raising one eyebrow very slowly. You might be tempted to ask, does this affect you? At ground level, almost certainly not in any dramatic sense. Earth's atmosphere absorbs harmful X-rays and extreme ultraviolet radiation efficiently. The magnetosphere deflects most charged particles. You remain blissfully cushioned by layers of physics doing their job. But the instruments don't lie. They're whispering now, across agencies, across continents. A network of sensors comparing notes. A star emitted something structured. Earth responded in kind. And here's a gentle joke the universe might be making. For centuries, humans feared the sun as an angry god. Now we monitor it with spacecraft worth billions of dollars, and when it does something slightly unusual, we respond not with panic, but with spreadsheets. Still, spreadsheets can be powerful, because as the data accumulates, one quiet realization spreads. This wasn't random noise. It wasn't instrument glitch. Multiple independent systems recorded the same synchronized signature. The sun sent a pattern pulse. And the instruments, faithful and patient, heard it. The day the data spike doesn't begin with drama. It begins with routine. You imagine the servers first, rows of them humming in climate control rooms, quietly digesting streams of solar measurements. Every second, satellites beam down torrents of numbers. Photon counts, magnetic flux densities, proton velocities, spectral intensities. Most of it flows into long-term archives, destined for careful analysis months or even years later. Solar science is often patient. The sun isn't going anywhere. Probably. But sometime after the pulse brushes Earth's magnetosphere, algorithms begin flagging correlations, not high-intensity alerts, not drop-everything notifications, just statistical anomalies. A synchronized rise in extreme ultraviolet flux at 17.1 nanometers, a concurrent microvariation in solar wind proton density, a matching oscillation in geomagnetic field strength measured in nanoteslas. Tiny units, barely perceptible against the constant background noise of Earth's magnetic chatter. Mainstream fact, Earth's magnetic field at the surface averages about 25 to 65 microteslas, depending on location. The fluctuation tonight, measured in fractions of a nanotesla, thousands of times smaller. In everyday terms, that's like noticing someone added a single grain of sugar to an Olympic swimming pool and somehow detecting it with a spoon. And yet, the pattern holds. Researchers overlay graphs from 3 separate observatories, one in space, one at the L1 Lagrange point, one ground base in Finland. The timestamps align almost perfectly, accounting for the 8-minute light travel time and the solar wind's slower particle speed. The spike isn't tall. It's sharp, clean edges, defined rise and fall. Solar flares typically produce chaotic curves, jagged peaks, irregular decay phases. Coronal mass ejections create broader disturbances lasting hours or days. This event is compressed, structured, almost symmetrical. Historians still argue whether earlier anomalies in archived solar data, particularly from the late 1990s, might represent similar compressed events that were dismissed as sensor calibration errors. Back then, instrumentation resolution was improving rapidly. It was easier to blame hardware than rewrite theory. Now, the models come out. Solar physicists rely on magnetohydrodynamics, MHD for short, to simulate how plasma behaves in magnetic fields. The equations are elegant and terrifyingly complex. They describe a star that is neither solid nor gas, but plasma, ionized particles dancing in magnetic loops. When magnetic reconnection occurs, field lines snapping and reconnecting, it releases energy explosively. That's the accepted explanation behind solar flares. But when the team runs preliminary simulations based on the measured amplitude and coherence of this pulse, something doesn't quite fit. Standard reconnection models produce turbulence. This event appears too coordinated. There's a quiet joke passed around in astrophysics circles. The sun didn't read our textbooks. It's said affectionately, because every time we think stellar physics is fully mapped, the sun improvises. In the ionosphere, radio operators notice a fleeting enhancement in high-frequency propagation. Amateur radio enthusiasts, yes, they still exist, lovingly tuning their equipment, report slightly extended range for about 12 minutes. One operator in Argentina manages to bounce a signal farther north than usual and posts about it online, assuming it's just favorable conditions. He has no idea he briefly surfed a solar anomaly. Somewhere, science nods approvingly at his accidental participation. Meanwhile, power grid operators receive automated space weather updates. Nothing alarming. No geomagnetic storm warnings. The Disturbance Storm Time Index, DST, which measures geomagnetic activity, barely twitches. For context, during the famous 1989 geomagnetic storm that caused the Quebec blackout, DST plunged dramatically negative. Tonight's variation is so minor, it doesn't even earn a headline, and yet the coherence persists in the data. There's also an intriguing footnote. Neutrino detectors, like Japan's Super Kamiokande, constantly measure neutrinos streaming from the sun's core, produced during nuclear fusion. These ghostly particles pass through Earth almost unaffected. Preliminary checks show no significant deviation in neutrino flux during the pulse. That's important. It suggests the core fusion rate remains steady. Whatever happened likely originated in the sun's outer magnetic layers, not at heart. That narrows the field. A fringe hypothesis reemerges in discussion threads. Could certain magnetic configurations temporarily channel energy in waveguide-like structures along coronal loops, producing cleaner emissions? It's speculative. Plasma is notoriously unruly. Trying to guide it neatly is like trying to braid a lightning bolt. Still, the graphs are persuasive. You picture a scientist zooming into the data, adjusting scales, smoothing noise filters on and off. Each time, the same shape appears. Rise, peak, fall, symmetry within milliseconds. Earth's magnetosphere responds with a faint echo, magnetospheric pulsations known as ULF waves, ultra-low frequency oscillations. They're common, but tonight, their onset aligns suspiciously well with the solar arrival time, like two metronomes briefly ticking together before drifting apart again. This is the moment when curiosity shifts from casual to focused. Emails begin circulating, not dramatic, just measured. Have you looked at the EUV channel from 1432 Universal Time Coordinated? Cross-check with L1 magnetometer. Possible instrumental artifact? Always that last question. Because extraordinary claims require extraordinarily boring verification. And here's the soft irony. If this pulse had been stronger, damaging satellites or sparking auroras over tropical beaches, it would be obvious. Instead, its subtlety makes it scientifically irresistible. It's a puzzle without chaos, a whisper with structure. By late evening, preliminary consensus forms. The spike is real, multi-instrument, multi-location, temporally consistent. The sun did something slightly new. You remain under the same familiar sky, perhaps noticing nothing more than a pleasant sunset. Rayleigh scattering still paints the horizon red. The atmosphere still bends light gently around Earth's curve. Birds still settle. Street lights flicker on. Above all that calm, a data set has changed. And somewhere in that shift lies the beginning of a new question. One that will pull researchers back to the sun's surface itself, searching for the origin of a pulse that refused to behave like any flare they've cataloged before. To understand why this pulse feels so unusual, you have to drift back toward something more familiar. The sun in one of its bad moods. Solar flares are the usual suspects. They erupt when magnetic field lines near sunspots twist, snap, and reconnect, releasing enormous bursts of energy. In seconds, they can unleash as much energy as billions of hydrogen bombs, though thankfully very, very far away. Flares are categorized by their X-ray brightness, measured by satellites like NOAA's GO series, which have monitored solar X-rays continuously since the 1970s. X-class flares are the heavyweights. M-class are medium. C-class are modest. A and B barely make headlines. You imagine standing on the sun's surface, ignoring the immediate vaporization problem for a moment. Beneath you, plasma boils at about 5,500 degrees Celsius. Towering loops of charged particles arch thousands of kilometers high, suspended by invisible magnetic tension. When reconnection happens, it's violent and messy. Radiation spikes across multiple wavelengths. Particles accelerate outward in chaotic sprays. Graphs look like seismographs during an earthquake. That's the key word, messy. The Carrington Event of 1859, the most famous solar storm in recorded history, followed this script. Astronomer Richard Carrington observed a brilliant white light flare on September 1st of that year. Less than 18 hours later, remarkably fast for a coronal mass ejection, Earth's magnetosphere was slammed. Telegraph systems sparked. Some operators reportedly received electric shocks. Auroras were seen as far south as the Caribbean. That's mainstream history, documented and dramatic. Tonight's pulse? No sparks. No glowing tropical skies. No telegraph operators dramatically unplugging equipment while shouting Victorian exclamations. Instead, the radiation signature is refined, coordinated, almost restrained. When scientists compare the spectral output of this event to archive flare data, they notice something missing. The broad-spectrum chaos typical of reconnection-driven flares. Yes, there is energy across ultraviolet and soft X-ray bands, but the intensity ratios are different. The rise and decay times are nearly symmetrical. Classic flares often show rapid rise and slower decay, like a clap of thunder fading into rumble. This pulse rises and falls like a breath. Historians still argue whether some minor 20th century subflares might have represented intermediate categories we never fully defined. The classification system itself evolved as instrumentation improved. Early astronomers saw only visible light changes. Later, X-ray monitoring reshaped definitions. It's possible we've been sorting solar events into slightly oversized boxes all along. There's also the matter of coronal mass ejections, CMEs. These massive expulsions of plasma can carry billions of tons of charged particles into space at speeds exceeding 1,000,000 miles per hour. They're usually associated with strong flares, though not always. When directed toward Earth, they can compress the magnetosphere and trigger geomagnetic storms. But during this pulse, coronagraphs, Telescopes that block out the sun's bright disk to observe the faint corona detect no significant CME, no giant bubble of plasma expanding outward, no halo signature indicating Earth-directed mass. It's as if the sun exhaled energy without throwing anything. That detail matters, because energy without bulk plasma suggests a different mechanism, perhaps a wave phenomenon rather than an explosive ejection. There's a quirky historical footnote here. In the early 20th century, before plasma physics matured, some astronomers speculated that the sun might emit structured electromagnetic tones tied to its magnetic cycles, almost like stellar music. The idea was poetic, if not rigorously testable at the time. Most of those papers faded into obscurity. But modern helioseismology, the study of pressure waves rippling inside the sun, has since confirmed that the sun does oscillate in complex patterns. We've mapped acoustic waves bouncing within it, revealing internal structures. So the concept of solar resonance isn't entirely whimsical. Still, resonance and radiation output? That's trickier. You follow the investigation back to the active region where the pulse appears to have originated. Sunspots cluster there, dark patches caused by intense magnetic concentration that inhibits convection, cooling those regions slightly compared to their surroundings. Galileo himself observed sunspots in the early 1600s, challenging belief that celestial bodies were perfect and unblemished. The sun, it turned out, had freckles. This particular active region doesn't look extraordinary in visible light. Moderate sunspot count, normal magnetic complexity, nothing screaming historic event incoming. Yet magnetograms, maps of magnetic field strength, reveal a tightly wound configuration, like a rubber band twisted just a bit further than comfortable. Instead of snapping violently, perhaps it adjusted. Magnetic field lines can shift topology without explosive reconnection. In laboratory plasma experiments, researchers sometimes observe smooth reconfigurations, rapid but not chaotic. Could the sun have undergone a large-scale, coherent magnetic adjustment? A kind of stellar stretch and sigh? The data from Parker Solar Probe's earlier switchback now seems more relevant. Those sudden magnetic reversals in the solar wind might be connected to deeper coronal processes. If a switchback formed near the source region and propagated outward, it could imprint a structured modulation on emitted radiation. Scientists tread carefully here. Correlation does not equal causation. That phrase echoes through every research meeting like a mantra. And yet, the absence of explosive flare characteristics combined with the presence of synchronized multi-band radiation suggests this pulse is not simply a weaker version of something familiar. It might represent a transitional behavior between flare and wave, between chaos and order. You can almost sense the sun resisting categorization. For centuries, humans feared solar wrath. Then we reduced it to equations and classes and tidy graphs. Now it sends a reminder. Stars are dynamic systems, not obedient light bulbs. Up above, the corona continues shimmering at over 1 million degrees, heated by mechanisms still debated. Some scientists argue nanoflares, tiny, frequent reconnection events, collectively sustain that heat. Others propose wave heating from Alfvén waves traveling along magnetic field lines. That debate remains open. Tonight's pulse nudges both camps. Because if magnetic waves can propagate cleanly enough to imprint synchronized radiation patterns, perhaps we've underestimated the sun's capacity for organized motion. You lie there, blissfully intact, shielded by atmosphere and magnetosphere, while researchers quietly redraw conceptual diagrams. No catastrophe, no apocalypse, just a star, behaving slightly differently than expected. And that, in science, is often far more exciting. So you drift outward again, past the familiar brightness of photosphere, beyond the churning granules the size of continents, and into the sun's outer atmosphere, the corona. It's faint during the day, invisible against the glare, but during a total solar eclipse it blooms into view, a pearly halo stretching millions of kilometers into space. Delicate, feathery, completely misleading, because the corona is outrageously hot. Mainstream fact. While the sun's visible surface sits at about 5,500 degrees Celsius, the corona soars to over 1 million degrees. In some regions, it reaches several million. That temperature inversion, hotter farther from the core, has puzzled scientists for decades. It's called the coronal heating problem. And despite progress, historians still argue whether the dominant mechanism is countless tiny magnetic reconnection events called nanoflares or wave-based heating from magnetohydrodynamic oscillations. The debate is lively. Solar physicists do not throw chairs, but they do raise eyebrows with passion. The pulse you're tracing appears to originate here, in the shimmering outer layer where magnetic field lines arc like luminous scaffolding. The corona isn't smooth. It's structured by magnetism, loops, streamers, plumes. Plasma flows along invisible rails, guided by fields anchored deep below in the sun's convective zone. Now imagine one of those loops, vast, glowing, suspended, suddenly adjusting, not snapping, not exploding, adjusting. Data from extreme ultraviolet imaging shows a brief brightening along a coronal loop near the active region identified earlier. The brightening is subtle, lasting only minutes, but its symmetry mirrors the radiation pulse detected at Earth. Rise, peak, fall. Coronal loops are known to oscillate. In fact, since the late 1990s, satellites like TRACE and later SDO have recorded loops swaying after flare events, vibrating like plucked guitar strings. These are often interpreted as standing Alfvén waves, oscillations traveling along magnetic field lines in plasma. They're real, measured, modeled. But here's the twist. Those oscillations usually follow explosive triggers. This time, the oscillation appears to be the event. You picture a loop under stress, magnetic tension building as differential rotation twists its anchored foot points. The sun doesn't rotate as a solid body. Its equator spins faster than its poles, a phenomenon called differential rotation, first documented in the 17th century by tracking sunspots. Over time, this shearing motion tangles magnetic fields into complex braids. Sometimes, those braids snap violently. Other times, perhaps, they slip into a lower energy configuration smoothly, releasing energy not as a chaotic burst, but as a coherent wave packet. That's one emerging hypothesis. And here's a quirky tidbit. In laboratory plasma chambers on Earth, tokamaks designed for fusion research, scientists have occasionally observed sudden, organized magnetic reconfigurations known as sawtooth oscillations. The plasma core temperature rises steadily, then drops abruptly as magnetic geometry shifts. It's not a perfect analogy, but some researchers can't resist drawing parallels. The sun, after all, is the ultimate fusion reactor, just significantly harder to install in your backyard. Back in the corona, spectroscopy reveals another clue. Specific ionized iron lines, commonly used to measure coronal temperatures, show a transient narrowing during the pulse. Line narrowing can indicate reduced turbulence in plasma motion. Reduced turbulence. That's unexpected. Solar eruptions usually increase turbulence, broadening spectral lines due to chaotic particle velocities. Reduced turbulence suggests temporary coherence. You float in imagination through that loop. Plasma glowing around you in ultraviolet hues your eyes can't naturally see. The magnetic field hums, not audibly but mathematically, vibrating with stored energy. Instead of ripping apart, it settles. The energy release propagates outward as a structured electromagnetic wave, imprinting that synchronized signature across multiple wavelengths. Historians still argue whether the corona behaves more like a turbulent ocean or a self-organizing system capable of spontaneous order. Turbulence theory predicts chaos. Yet plasma physics often reveals emergent structures, filaments, sheets, vortices, that seem almost intentional in their geometry. The pulse may be evidence of such emergent order. Meanwhile, coronagraph images show no expanding CME bubble. The solar wind speed remains steady around 400 kilometers per second in that region. Typical slow wind values. No dramatic acceleration. No plasma cloud barreling toward Earth. It's like the sun flexed a muscle without throwing a punch. There's also the matter of magnetic helicity, a measure of how twisted magnetic field lines are. Helicity is conserved in many plasma processes, meaning it can't simply vanish. It must redistribute. Some models suggest that when helicity reaches a threshold, the system can reorganize globally rather than locally. Instead of one violent snap, you get a coordinated relaxation, a stellar stretch, and maybe, just maybe, that stretch sent the pulse. Up above, the Parker Solar Probe continues its daring orbits, dipping closer with each pass. During one perihelion, it actually flew through coronal streamers, sampling plasma directly. Its instruments measure electric and magnetic field fluctuations at astonishing resolution. Cross-referencing its earlier switchback detection with this coronal loop brightening reveals timing that is suggestive, not proof, but compelling. You might smile at the thought that while you're trying to get comfortable under a blanket, a spacecraft is literally skimming the atmosphere of a star, braving temperatures that would liquefy steel. Perspective is humbling. The corona shimmers on, appearing tranquil from afar. But beneath that calm glow lies a system capable of sudden coherence, magnetic choreography rather than magnetic chaos. And as researchers zoom in on coronal imagery frame by frame, adjusting contrast, enhancing faint structures, they begin to suspect that this pulse didn't begin as a flare at all. It began as a rebalancing, a brief, elegant correction in the architecture of a star. If the corona is the stage, then magnetism is the script. You sink deeper now, not into heat, but into invisible structure. The sun is, at its core, a magnetic machine. Its magnetic field isn't static or tidy like a bar magnet you stick to a fridge. It's generated by a dynamo process deep inside, where electrically conductive plasma churns and rotates. The sun's differential rotation, faster at the equator, slower at the poles, twists magnetic field lines over time, winding them like elastic bands stretched to their limit. Mainstream fact. Approximately every 11 years, the sun's magnetic poles flip. North becomes south. South becomes north. This solar cycle is tied to the waxing and waning of sunspot numbers. At solar maximum, the magnetic field is most tangled, complex, and energetic. We are currently near such a maximum, which means the sun's magnetic environment is, scientifically speaking, spicy. Now imagine billions of kilometers of magnetic field lines threading through plasma, constantly pulled, stretched, braided. They store energy in their curvature and tension. When they reconnect explosively, we get flares. When they open outward, we get high-speed solar wind streams. But what happens when an entire magnetic lattice shifts subtly, globally, without snapping? That's the question hovering over tonight's pulse. Magnetograms from the active region show a rapid but smooth change in magnetic shear. Shear describes how much neighboring magnetic field lines differ in direction. High shear often precedes flares. But in this case, the shear decreases during the pulse, as if tension is being redistributed instead of violently released. It's like watching a tightly twisted rope slowly unwind rather than break. Historians still argue whether large-scale magnetic reorganizations, sometimes called global reconfigurations, occur more often than we detect, because unless they produce dramatic flares or CMEs, they can slip beneath observational thresholds. Only with modern high-cadence imaging have we begun to notice subtle, system-wide adjustments. And here's where things grow particularly intriguing. Earth's magnetosphere has its own natural oscillations, standing waves triggered by interactions with the solar wind. These are called field line resonances. Under certain conditions, if incoming solar wind fluctuations match the natural frequency of Earth's magnetic field lines, resonance can amplify the oscillation. Think of pushing a child on a swing. Timed correctly, small pushes build larger motion. Tonight's solar pulse carries a frequency component that closely matches one of Earth's common magnetospheric resonance bands. The match isn't perfect, but it's unusually close. That might explain the synchronized PC1 and ULF waves recorded earlier. Coincidence? Possibly, but physicists have long known that plasma systems can couple across space via magnetic fields. In fact, the concept of magnetic connectivity is central to space weather research. Field lines from the sun can link directly into Earth's magnetosphere under favorable orientations, particularly when the interplanetary magnetic field points southward. This alignment allows energy transfer through a process called magnetic reconnection at Earth's magnetopause. In this event, however, the interplanetary magnetic field wasn't strongly southward. It was moderate, stable, which makes the coherence even more puzzling. There's a fringe but fascinating idea occasionally floated in theoretical circles, that large plasma systems may exhibit self-organized criticality. In such systems, small changes can propagate across scales, producing coordinated adjustments without a single explosive trigger. The concept has been applied to everything from sandpile avalanches to solar flare distributions. Maybe tonight's pulse is an example of the sun reaching a critical magnetic threshold and readjusting smoothly. You picture the solar magnetic field like an enormous, invisible web. At one node, tension shifts. The adjustment ripples outward, not as chaos, but as alignment, a recalibration. The Parker Solar Probe's earlier switchback event now seems less isolated. Switchbacks are sudden reversals in magnetic field direction within the solar wind. They were first observed decades ago, but only recently studied up close. Some researchers believe they originate from kinks in coronal magnetic fields that propagate outward. If one particularly coherent switchback formed during this coronal reconfiguration, it might have carried that structured signature all the way to Earth's orbit. And then there's the solar dynamo itself. Deep inside the sun, convection currents transport heat outward while the entire star rotates. These motions generate magnetic fields through complex fluid dynamics described by dynamo theory. Yet despite decades of modeling, the precise mechanics of the solar dynamo remain partly mysterious. Simulations can reproduce general cycles, but fine-scale behavior often diverges from observation. Historians still argue whether subtle changes in the dynamo's internal flow patterns could produce temporary surface coherence events like this one. Because we can't see directly into the sun's interior, we infer structure through helioseismology, measuring pressure waves reverberating inside. It's like diagnosing a bell by listening to how it rings. And maybe, just maybe, tonight the sun rang differently. Back on Earth, magnetometers continue their patient recording. The resonance fades quickly. Within an hour, field values settle into baseline fluctuations. The ionosphere relaxes. Radio propagation returns to normal. The data spike remains, a clean notch in an otherwise ordinary day. You're still safe, wrapped in atmosphere and iron core shielding, blissfully unaware that 150 million kilometers away, magnetic fields twisted and then agreed, briefly, on a new arrangement. There's something almost comforting about it. Not every adjustment in the universe is violent. Not every release of tension ends in explosion. Sometimes, even a star finds a smoother way to rebalance. And as scientists begin drafting preliminary notes about magnetic shear reduction and resonance alignment, one thought quietly forms. If this was a global magnetic recalibration, what does that mean for the rest of the solar cycle? Because cycles imply continuation, and the sun is not done turning. If what you just witnessed was a magnetic recalibration, rather than flare, then you're standing at the edge of a naming problem. Science loves categories. We classify clouds, earthquakes, hurricanes, even pasta shapes with impressive enthusiasm. Solar activity is no exception. We have flare classes, geomagnetic storm scales, radiation storm levels, all neat, all labeled, all designed to turn a chaotic star into something spreadsheet-friendly. But tonight's pulse doesn't fit cleanly anywhere. You imagine a quiet meeting, virtual of course, where solar physicists share screens filled with plots and magnetograms. Someone clears their throat and says, "It's not a flare." Someone else adds, "It's not a CME." A third suggests cautiously, "It resembles a wave-driven emission event." And then everyone pauses because naming something is dangerous. Once you name it, you imply you understand it. Mainstream fact, new classifications in solar physics don't happen often. The X-ray flare scale was formalized in the 1970s when continuous satellite monitoring became available. Before that, flares were categorized visually in H-alpha wavelengths. As instrumentation improved, definitions evolved. So the idea that we might need a new subclass is absurd. It's just rare. Data comparisons begin stretching backward through decades of archives. Machine learning tools comb through terabytes of historical solar records, searching for similar synchronized radiation patterns. A few near matches appear, events from 2003 and 2014, but none display the same degree of multiband symmetry combined with magnetic shear reduction. Historians still argue whether we've undercounted subtle solar phenomena simply because they weren't dramatic enough to trigger alarms. Big storms get attention. Quiet anomalies get footnotes. But this one keeps resurfacing in the algorithms. There's a tentative phrase floating around, coherent solar pulse. Not official, not published, just whispered in draft emails and lab discussions. It captures the essence, structured, wave-like, magnetically synchronized. Meanwhile, Earth's upper atmosphere continues to show faint aftereffects. Satellite drag measurements, used to monitor how much the atmosphere expands under solar heating, indicate a slight, temporary density increase at mid-latitudes. Not enough to alter satellite orbits significantly, but measurable. The thermosphere, heated by ultraviolet radiation, puffed outward just a little more symmetrically than usual. That symmetry again. You might picture Earth's atmosphere breathing in response to the sun's breath, not gasping, just inhaling gently. There's also renewed interest in a concept called magnetoseismology, the study of magnetic oscillations across planetary environments. Just as seismology uses earthquakes to probe Earth's interior, magnetoseismology uses magnetic waves to infer properties of plasma systems. If the sun emitted a coherent magnetic wave packet and Earth responded with resonant oscillations, this event could serve as a natural experiment linking stellar and planetary magnetism. It's the kind of thing that makes space physicists quietly giddy. Of course, skepticism remains healthy. Some researchers caution that statistical coincidence cannot be ruled out. With enough data channels, patterns will occasionally align by chance. Correlation, as always, does not equal causation. The mantra returns. And then there are the fringe thinkers, those who see in this pulse evidence of deeper stellar cycles beyond the standard 11-year rhythm. A few resurrect the idea of quasi-biennial oscillations, secondary cycles superimposed on the main solar cycle. Others speculate about magnetic Rossby waves, large-scale waves influenced by rotation, similar to atmospheric Rossby waves on Earth that shape jet streams. Rossby waves in the sun are real, observed in helioseismic data. But whether they can produce coherent radiation pulses remains debated. You can almost hear the gentle academic sparring. Wave-driven heating proponents pointing at the spectral narrowing. Reconnection specialists emphasizing localized magnetic complexity. Dynamo theorists suggesting deeper flow changes. No shouting, just careful, caffeinated disagreement. And hovering above it all is the practical question. Does this matter for space weather forecasting? For now, the answer seems to be no, at least not in a disruptive sense. The pulse caused no geomagnetic storm, no satellite failures, no grid instability. But understanding subtle solar behavior is crucial, because sometimes small events precede larger ones. In earthquake science, minor tremors can signal stress redistribution along faults. In plasma systems, coherence can indicate thresholds being approached. Historians still argue whether certain large solar superstorms were preceded by quieter magnetic reorganizations days earlier. Data from the Carrington era is sparse, but some ice core records hint at complex pre-event signatures. So researchers watch. You imagine the sun rotating, carrying the active region slowly across its disk. In about 27 days, it will face Earth again unless it decays first. Sunspots often dissipate within days or weeks. Magnetic fields untangle. Surface patterns shift. But if this region produces another coherent pulse on its next rotation, that would be hard to dismiss as coincidence. Down here, you feel none of that tension. The night is calm. The planet hums with its usual electricity. Servers, streetlights, refrigerators doing their loyal buzzing. Overhead, satellites continue their patient loops, silently collecting the next stream of numbers. Science stands at a gentle crossroads. Either this was a statistical curiosity, or it's the first documented instance of a new subclass of solar activity. And if it is new, you're living in the moment when the sun quietly expanded our vocabulary, not with a bang, with a pulse. While scientists debate naming rights for a star's polite rearrangement, Earth is busy responding in its own understated way. You drift downward now, from magnetosphere to thermosphere to ionosphere, the layered architecture of air that shields you every second of your life without asking for applause. The atmosphere isn't just a blanket of gas. It's an active electrical environment. Solar radiation constantly ionizes atoms high above, knocking electrons free and creating a shimmering region of charged particles. Mainstream fact. The ionosphere begins roughly 60 kilometers above Earth's surface and extends up to about 1,000 kilometers. It's crucial for radio communication because it reflects certain frequencies back to the ground, allowing signals to travel beyond the horizon. During strong solar flares, sudden ionospheric disturbances can disrupt shortwave radio across entire continents. Tonight's response is gentler. Instruments called ionosons, basically atmospheric sonar for electrons, detect a slight elevation in the F region's critical frequency at mid-latitudes. That means the ionosphere briefly becomes more capable of reflecting higher frequency radio waves. It's subtle, lasting less than 15 minutes. If you weren't measuring carefully, you'd miss it. But the timing lines up again. The structured pulse arrives. Ionization increases in a narrow band. Then it relaxes, almost symmetrically, like a tide rising and falling on cue. You imagine electrons being nudged into higher energy states by ultraviolet photons, arriving in coordinated bursts. Not chaotic bombardment, more like a synchronized tap on millions of microscopic shoulders. Further down, in the stratosphere, nothing dramatic happens. Ozone absorbs much of the incoming ultraviolet radiation, as it always does. The ozone layer, discovered in 1913 by French physicists Charles Fabry and Henri Buisson, acts as a chemical shield, filtering harmful wavelengths. Without it, life on land would struggle. Tonight, it performs flawlessly, unaware of participating in a cosmic experiment. Historians still argue whether prolonged variations in solar ultraviolet output significantly influence long-term climate patterns. The consensus is that solar variability plays a role, but it's far smaller than modern greenhouse gas forcing. Still, subtle UV shifts can affect stratospheric chemistry in measurable ways. The sun has fingerprints everywhere, even when it whispers. Back in the upper thermosphere, satellite drag data shows that slight atmospheric expansion mentioned earlier. When solar radiation heats the thermosphere, it puffs outward, increasing drag on low Earth orbit satellites. During intense solar storms, this can shorten satellite lifespans. In 2022, a moderate geomagnetic storm increased atmospheric drag enough to cause dozens of newly launched small satellites to re-enter prematurely. Space is glamorous until air resistance ruins your orbit. Tonight's heating is mild, but it's oddly uniform across certain latitudes, matching the pulse's frequency envelope. Engineers notice, log it, move on, and then there are the auroras. Normally confined to polar regions where Earth's magnetic field lines converge, auroras form when charged particles collide with atmospheric gases, exciting oxygen and nitrogen into glowing states. Green is common, emitted by oxygen around 100 kilometers up. Red auroras occur higher, above 200 kilometers, when oxygen glows at lower densities. During this event, faint auroral arcs appear slightly farther from the poles than models predicted. Nothing spectacular, but measurable in all-sky camera networks. The arcs are thin, subtle, briefly intensified along a band consistent with that earlier resonance frequency. It's as if the magnetosphere hummed and the sky answered. You picture someone in southern Canada glancing up and noticing a slightly brighter green ripple than usual, assuming it's just a nice night. Meanwhile, magnetometers quietly confirm a synchronized oscillation in the same frequency range detected earlier. There's also an intriguing biological footnote, though it remains speculative. Some studies suggest migratory birds and certain marine animals detect geomagnetic fluctuations for navigation. The mechanisms aren't fully understood, but magnetoreception appears real. Could a brief, low-amplitude magnetic resonance influence orientation behaviors? Probably not in any meaningful way at this scale. But the question floats there, curious and unresolved. Science is careful not to anthropomorphize too much. The Earth doesn't feel the sun. It responds according to physics. Plasma interacts with magnetic fields. Atoms absorb photons. Electrons jump energy levels. And yet the coordination of it all feels almost conversational. Solar pulse, magnetospheric resonance, ionospheric ripple, auroral shimmer, a chain reaction delicately linked. Meanwhile, GPS signals pass through the ionosphere slightly refracted. Timing corrections compensate automatically. Airplanes navigate. Ships steer. You scroll or stretch or slowly drift toward sleep. Civilization continues uninterrupted. That's the quiet triumph of Earth's shielding systems. The magnetosphere deflects most charged particles. The atmosphere absorbs high-energy radiation. Layers upon layers of protection evolved or formed over billions of years. Mars, lacking a global magnetic field, lost much of its atmosphere to solar wind erosion long ago. You, fortunately, are standing on the better shielded option. Historians still argue whether early Earth's magnetic field was weaker or stronger than today's, and how that influenced atmospheric retention. But what's certain is this. Without magnetic protection, complex life would face a harsher radiation environment. Tonight, that shield flex gently. The pulse fades. Electron densities normalize. Auroral arcs dim. Satellites continue their steady loops, reporting nominal status. The magnetosphere returns to its background rhythm. Substorms, fluctuations, the constant dance with solar wind. Yet the data remains archived. A small, coherent disturbance that links star and planet in a measurable chain. Not destructive, not transformative, just different. And different, in science, is the doorway to understanding. The auroras linger longer in memory than in the sky. You picture the curve of Earth at night. City lights tracing continents, oceans swallowed in darkness, and above the poles, those familiar veils of green. Usually, they cling close to high latitudes, shaped like glowing crowns around the Arctic and Antarctic circles. But tonight, they stretch just a little farther. Not dramatically. No tropical auroras lighting up beach vacations. But camera networks in Scotland, northern Germany, and parts of northern United States capture faint arcs dipping lower than forecast models suggested. The KP index, a standard measure of geomagnetic activity, ranging from 0 to 9, barely nudges upward. Officially, conditions remain quiet to unsettled. And yet, the shapes look organized. Mainstream fact. Auroras form when charged particles from the solar wind spiral along Earth's magnetic field lines and collide with atmospheric gases. Oxygen produces green and red light. Nitrogen can create purples and blues. The altitude determines the color and intensity. Most auroras pulse irregularly, flickering as particle precipitation varies. Tonight's arcs pulse rhythmically. All sky imagers record a faint oscillation in brightness at a frequency matching the earlier magnetospheric resonance. It's subtle, visible mainly in time-lapse analysis rather than the naked eye, but the synchronization persists for several minutes. You imagine standing under that sky, The air is cold, maybe crisp with winter dryness. A soft green ribbon hangs above the horizon, gently brightening and dimming like a slow heartbeat. If you didn't know better, you'd call it beautiful and move on, which is exactly what most people do. But magnetometers beneath that same sky record PC1 pulsations, ultra-low frequency waves in Earth's magnetic field, occurring in lockstep with the auroral brightness changes. It's as if the magnetosphere and ionosphere are sharing a quiet rhythm section. Historians still argue whether certain historical reports of pulsating auroras might reflect similar resonant interactions rather than purely chaotic solar storms. In the 18th and 19th centuries, observers described auroras that throbbed or breathed. Without magnetometers, they relied on poetic language. Now we have data to accompany the poetry. There's also a fascinating tidbit tucked into auroral research. Pulsating auroras are often linked to interactions with plasma waves called Cor's waves in the magnetosphere. These waves can scatter energetic electrons into the atmosphere in periodic bursts. Cor's waves were first detected in the 1960s and are named because, when converted to audio frequencies, they sound like birds chirping at dawn. Space, apparently, has its own morning soundtrack. Tonight's pulsation frequency doesn't match classic chorus wave patterns perfectly. It aligns more closely with the incoming solar modulation. That's unusual. Up above, satellites in polar orbit pass through the auroral oval, directly sampling particle precipitation. They measure electron flux increases that rise and fall smoothly rather than spiking erratically. Smooth curves again. Symmetry again. You might smile at the thought that the sun sent a pattern signal, and the sky replied with synchronized light. Not intentional. Just physics resonating across space. Down at lower latitudes, sky watchers check social media. A few photos trend briefly. Aurora visible farther south tonight. But without dramatic intensity, the story doesn't explode into headlines. No viral spectacle. Just a handful of long exposure shots capturing faint green arcs over pine trees and rooftops. And that's part of what makes this event so intriguing. It's scientifically rich but visually restrained. The universe showing off in whisper mode. Meanwhile, researchers overlay auroral camera timestamps with satellite particle data and magnetometer readings. The correlations tighten. The frequency coherence persists across systems. It's no longer just a solar observation. It's a star-planet interaction captured in synchronized datasets. Mainstream models of geomagnetic storms emphasize large-scale solar wind pressure increases and strong southward interplanetary magnetic fields. Neither condition was extreme tonight. Solar wind speed remained moderate. Density fluctuations were minor. The IMF orientation wasn't dramatically southward. So why the organized auroral response? One possibility emerges. Even small amplitude solar magnetic oscillations, if frequency matched to magnetospheric resonances, can produce disproportionately coherent atmospheric effects. In other words, it's not about strength, it's about timing. Think of pushing someone on a swing again. A gentle push, perfectly timed, can be more effective than a stronger shove at the wrong moment. There's also renewed attention on field line resonances, standing waves along Earth's magnetic field lines stretching from pole to pole. These lines have natural frequencies determined by plasma density and magnetic strength. If the solar pulse contained energy at one of those frequencies, resonance could amplify the oscillation locally. Historians still argue whether we've underestimated the role of resonance in moderate space weather events because dramatic storms steal the spotlight. Tonight suggests subtle coupling deserves more respect. You lie beneath a planet quietly humming in magnetic harmony. The auroras fade back toward the poles. The oscillations dampen. Within an hour, the sky returns to its usual darkness punctuated by stars that, for now, behave predictably. But in research labs, excitement simmers, because the auroras provided visual confirmation that the pulse wasn't just an instrumental quirk. It left a luminous fingerprint across the atmosphere, a coordinated dance of electrons and light. And as Earth settles back into baseline rhythms, attention turns again to the star itself. Because if a gentle magnetic hum can travel 150 million kilometers and orchestrate a planetary light show, what might a stronger, equally coherent pulse do next time? The sun continues rotating, magnetic fields still in motion, and you, under fading green ribbons, remain blissfully unaware that you just witnessed the softest kind of cosmic duet. While the auroras perform their quiet ballet, engineers do something far less poetic. They open dashboards. You descend now from glowing skies into control rooms filled with fluorescent light and ergonomic chairs. Modern civilization hums on electricity, power grids stretching across continents, transformers stepping voltage up and down like disciplined acrobats. And those grids, elegant as they are, have a known vulnerability: geomagnetically induced currents. Mainstream fact: during a March 1989 geomagnetic storm, induced currents overloaded Quebec's power grid, causing a province-wide blackout that lasted 9 hours. 6 million people lost electricity because the sun decided to rearrange its magnetic furniture. Transformers are particularly sensitive because fluctuating magnetic fields can induce direct currents in long transmission lines, overheating equipment never designed for that kind of stress. Tonight, grid operators watch carefully. Space weather centers issue routine updates. Solar wind speed, moderate. IMF orientation, stable. KP index, low. Officially, nothing to worry about. But subtle magnetometer readings show those brief oscillations you've been following. They're small, far below thresholds associated with infrastructure damage, but precise. Engineers zoom in on real-time geomagnetic disturbance maps. They look like gentle ripples rather than storms. The oscillations are periodic, matching the earlier resonance frequency. Induced currents do appear in long transmission lines at high latitudes, but they are minuscule, well within tolerance. It's like feeling the faint vibration of a truck passing several streets away. Noticeable if you're listening for it. Harmless otherwise. You might chuckle at the contrast. Scientists debate new classifications while grid operators sip coffee and confirm everything is nominal. Nominal is one of those words that sounds boring, but secretly means the planet still works. There's also the satellite industry to consider. Thousands of satellites orbit Earth now. Communication arrays, weather monitors, navigation systems, research platforms. They operate in regions where charged particles can accumulate on surfaces, creating differential charging. During strong solar storms, that buildup can discharge suddenly, damaging electronics. But particle flux levels tonight remain low to moderate. The coherent pulse-carried structure, not brute force. Radiation monitors aboard geostationary satellites show only slight, symmetrical variations. No anomalies in onboard systems. Historians still argue whether subtle, repeated magnetic oscillations could have cumulative effects on satellite components over long timescales. It's difficult to isolate variables in orbit. Space is already a harsh environment. Thermal cycling, micrometeoroids, cosmic rays. A faint magnetic hum probably ranks low on the list of concerns. Airlines, too, keep an eye on solar conditions. High-frequency radio communication used on polar routes can degrade during solar events. Increased radiation exposure at cruising altitude becomes a factor during major storms. But tonight's event barely nudges atmospheric radiation levels. Dosimeters aboard high-altitude flights record nothing unusual. The world continues. And yet, researchers in space weather forecasting centers are intrigued. Because if coherent pulses can couple efficiently with Earth's magnetosphere without requiring extreme solar wind pressure, forecasting models may need refinement. Current models emphasize magnitude, how strong the solar wind is, how southward the magnetic field points. Less emphasis is placed on frequency content and resonance potential. Tonight suggests timing matters more than previously appreciated. There's a quirky historical parallel here. In the early days of radio engineering, operators noticed mysterious signal fading and interference patterns long before plasma physics explained the ionosphere's behavior. They knew something was happening. They just didn't have the theory yet. Practical observation often precedes theoretical clarity. You imagine a young engineer somewhere adding a note to a report. Observed low-amplitude, frequency-coherent geomagnetic oscillations correlate with solar EUV modulation. It sounds dry. It's actually fascinating, because power grids are like giant antennas stretched across landscapes. Long conductive lines naturally interact with geomagnetic fluctuations. Most of the time, those fluctuations are random enough to average out, but coherent oscillations, even small ones, could theoretically resonate with certain line lengths. Tonight's amplitude is far too low for that to matter, but the concept lingers. Historians still argue whether the Carrington Event would cause catastrophic damage if repeated today. Studies suggest widespread transformer failures are possible in worst-case scenarios. That's why monitoring subtle solar behavior matters. Not because tonight was dangerous, but because understanding small events builds predictive skill for larger ones. Back in orbit, GPS satellites adjust for minor ionospheric delays automatically. Financial markets tick on. Data centers hum. Refrigerators continue their noble mission of preserving leftovers. You remain blissfully cushioned by infrastructure designed with solar temper tantrums in mind. And here's the gentle irony. The sun just demonstrated a new trick, coherence over chaos, and it barely disturbed your Wi-Fi. The apocalypse will have to wait. Still, space weather scientists lean forward because the event challenges assumptions. It suggests that magnetic resonance effects might amplify certain interactions even when traditional storm indicators remain low. A star whispered. The planet hummed. Civilization noticed, just barely, and somewhere in the back of every monitoring center, a quiet thought forms. If this was a soft version, what would a louder, equally synchronized pulse look like? The dashboards returned to steady lines. Oscillations dampened. Systems remained stable. But the models, those intricate mathematical representations of star-planet interaction, are about to receive a small but meaningful update, because sometimes the most important changes arrive without breaking anything at all. Beyond power grids and auroras, there's another invisible web wrapped around your planet. Signals. Radio waves arc between continents. Satellite transmissions beam television, internet, weather data. Deep space probes whisper back from billions of kilometers away. You live inside an electromagnetic ecosystem, so constant you barely notice it. Until something flickers. Tonight, something flickers. Not dramatically. No lost GPS. No dropped calls you can blame on the sun instead of your carrier. But sensitive monitoring stations detect slight, synchronized fluctuations in high-frequency radio propagation. The ionosphere, still gently perturbed by the coherent pulse, refracts signals a little differently for a short time. Mainstream fact. Radio communication in the 3 to 30 megahertz range relies heavily on ionospheric reflection. During strong solar flares, sudden ionospheric disturbances can cause radio blackouts on the sunlit side of Earth. These are classified on a scale from R1 minor to R5 extreme. Tonight doesn't even register as R1, and yet the pattern is measurable. Amateur radio operators, those patient hobbyists who treat the sky like a playground, report brief, unusually stable long-distance contacts. Signals bounce cleanly, less fading, a smoother path. It's subtle, but enough for a few enthusiasts to post. Propagation oddly good tonight. They have no idea they're sampling a solar experiment. Meanwhile, satellite communication engineers notice faint phase shifts in signals passing through the upper atmosphere. GPS relies on precise timing. Atomic clocks aboard satellites synchronize a billionth of a second. Even tiny ionospheric delays must be corrected. The system is designed for this. Algorithms compensate automatically. Still, logs record the anomaly. Historians still argue whether subtle solar-induced timing variations might accumulate into measurable biases in long-duration space missions. For Earth-based systems, corrections are routine, but for probes navigating the outer solar system, precision matters profoundly. A microsecond here, a kilometer there. Space is vast, small errors stretch. Further out, NASA's Deep Space Network, massive radio antennas in California, Spain, and Australia, listens to faint spacecraft transmissions. Charged particles in space can cause scintillation, rapid fluctuations in signal amplitude and phase. Tonight's solar wind density remains stable, but embedded within it is that coherent magnetic ripple. And for a few minutes, certain deep space signals exhibit a faint periodic modulation, not enough to disrupt communication, just enough to show up in Fourier analysis, mathematical decomposition of signals into frequency components. The same frequency again. You begin to appreciate how pervasive resonance can be. It threads through magnetospheres, ionospheres, transmission lines, radio paths. A shared tempo across systems that normally operate independently. There's also an intriguing atmospheric effect known as traveling ionospheric disturbances, TIDs. These are wave-like structures in the ionosphere that propagate horizontally, often triggered by geomagnetic activity or even lower atmosphere weather systems. During this event, GPS total electron content maps show a faint, ring-like disturbance spreading from high latitudes toward mid-latitudes, synchronized with the pulse's arrival. It's as if the upper atmosphere briefly rippled outward, like a pond touched by a single, precise pebble. Some researchers speculate whether the coherent solar pulse acted as that pebble, injecting energy at just the right frequency to launch a mild global TID. It's plausible. It's also challenging to prove. Atmospheric systems are noisy, influenced by countless factors, from solar radiation to tropospheric storms. Correlation does not equal causation. The mantra returns again, like a lullaby for cautious scientists. There's a quirky historical note here. During World War II, radar operators sometimes detected mysterious signal anomalies later traced to solar activity. At the time, understanding of solar-terrestrial coupling was limited. The sun, it turned out, was occasionally jamming both sides indiscriminately. Equal opportunity interference. Tonight, though, the sun behaves less like a jammer and more like a metronome. Signals wobble gently in time. In low Earth orbit, CubeSats, small, shoebox-sized satellites, carry student-built experiments. Some of them include simple magnetometers and radiation detectors. Data from a handful of these tiny platforms confirms the same low-amplitude oscillation seen by their larger, more expensive cousins. There's something charming about that. Student projects inadvertently contributing to cutting-edge solar research. Space, after all, doesn't discriminate by budget. As the minutes pass, the ripple fades. Electron densities settle. Radio propagation returns to baseline variability. Deep space signals smooth out. If you weren't looking, you'd never know anything happened. But researchers are looking. They begin to piece together a timeline. Coronal loop brightening, magnetic shear reduction, structured radiation pulse, magnetospheric resonance, auroral synchronization, ionospheric ripple, signal phase modulation, a chain reaction spanning 150 million kilometers, completed in under an hour. Historians still argue whether we fully appreciate how tightly coupled stellar and planetary systems can be on subtle scales. Dramatic solar storms are obvious, but tonight demonstrates that even modest, coherent emissions can orchestrate measurable, planet-wide responses. You remain at the center of it all, wrapped in atmosphere and Wi-Fi signals, blissfully unaware that for a brief window, every layer above you hummed in faint synchrony with a star. It's not catastrophic. It's not even disruptive. It's elegant, and elegance in physics often hints at deeper structure waiting to be understood. Now you turn inward, not just toward Earth, not just toward the sun, but toward yourself. Because whenever something cosmic happens, even quietly, someone eventually asks the inevitable question, does this affect us? You lie there, breathing slowly, heart pacing its own steady rhythm. Your body runs on electrical signals, neurons firing through carefully maintained voltage gradients. The human nervous system depends on ion channels opening and closing in precise timing. Tiny currents pass along axons. The heart's sinoatrial node generates rhythmic pulses that keep blood moving. You are, in a sense, a bioelectric organism living inside a planetary magnetic field. Mainstream fact: Earth's magnetic field at the surface ranges between about 25 and 65 microteslas. Your body evolved entirely within that range. It's always been there, shielding, steady, unremarked. Studies have explored whether geomagnetic fluctuations influence human physiology. Most large-scale analyses find no strong, consistent effects on health from minor geomagnetic disturbances. During major storms, some research has suggested slight correlations with cardiovascular events, but causation remains debated. Historians still argue whether correlations between geomagnetic storms and biological responses reflect direct magnetic influence or secondary factors, like changes in atmospheric electricity or even human stress reactions to technological disruptions. Tonight's oscillations are far smaller than major geomagnetic storms. Measured in fractions of nanoteslas, they're orders of magnitude below what would meaningfully perturb cellular processes. Your neurons continue firing on their own internal schedule, blissfully indifferent to the sun's coherent pulse. And yet, there's something poetic about the idea that the same magnetic resonance rippling through the magnetosphere also passes through you. No effect, just passage. There's a quirky tidbit here. Some migratory animals, birds, sea turtles, even certain bacteria, possess magnetoreception, the ability to sense Earth's magnetic field. One leading hypothesis involves a protein called cryptochrome, which may form quantum-sensitive radical pairs influenced by magnetic orientation. It sounds like science fiction, but experiments suggest weak magnetic fields can subtly influence these chemical reactions. Could a tiny, coherent magnetic oscillation briefly nudge such systems? Probably not in any behaviorally meaningful way at this amplitude, but the possibility reminds you how intertwined life and magnetism truly are. Your circadian rhythm, for instance, is primarily governed by light. Sunlight setting the clock in your brain's suprachiasmatic nucleus. Solar radiation has shaped sleep patterns, hormone cycles, seasonal behaviors for millions of years. The sun dictates waking and rest far more than its magnetic whispers ever could. Still, researchers occasionally examine whether geomagnetic quiet versus stormy days correlate with mood variations. Results are mixed. Human psychology is complicated enough without blaming the sun for a bad Monday. Tonight, nothing in emergency room spikes. No global headaches. No mysterious wave of synchronized yawning, though that might actually be charming. The pulse has already faded from Earth's magnetic readings. The auroras have dimmed. The ionosphere has settled. And you remain warm, oxygenated, intact. But now the pacing shifts. The scientists who track the event begin drafting preliminary papers. Titles form cautiously. Observation of coherent multiband solar emission event with magnetospheric resonance. It's not flashy. It's accurate. They will debate terminology for months. They will test models, rerun simulations, compare historical datasets. Conferences will feature polite arguments and laser pointer gestures at spectrographs. And slowly, this quiet pulse will find its place in the broader understanding of solar behavior. You imagine the sun rotating, that once active region slipping toward the limb. In a few days, it will disappear from direct view, carried to the far side. But helioseismology, using acoustic waves traveling through the sun, will continue mapping active regions even when hidden. We can see through the star now, in a way Galileo could never have imagined. Historians still argue whether humanity has entered a new era of stellar intimacy, where our monitoring is so continuous that the sun can scarcely twitch without us noticing. And perhaps that's what makes tonight special. Not that the sun did something dangerous, but that it did something subtle, and we heard it. The pacing slows now. The excitement of data spikes, softens into reflection. The universe feels less like a threat and more like a conversation partner. Vast, yes, but measurable. Knowable, at least in fragments. You breathe in. The same star that powered ancient photosynthesis, that warmed dinosaurs, that rose over first human settlements, just sent a structured whisper across space. It brushed your planet's magnetic shield, shimmered through your atmosphere, rippled faintly in signals and sky, and you slept through most of it. That's not ignorance. That's stability. The sun continues to shine with steady fusion in its core, hydrogen becoming helium, mass becoming energy, photons beginning journeys that will take thousands of years to reach the surface and 8 minutes more to reach you. Tonight's pulse is already dissolving into history, archived in datasets, plotted on graphs, debated in papers. You remain beneath a star that is both predictable and capable of surprise. And as your thoughts slow, as the hum of Earth's magnetic field fades back into background silence, you feel something almost comforting. The universe can change without breaking you. The sun can rearrange itself without demanding your fear. Magnetic fields can hum across space, and life can continue breathing. The pulse is over. The night is steady. And you are safe beneath a star still turning, still shining, still quietly rewriting what we thought we knew. Long before satellites, before magnetometers and spectrographs, you would have looked up at the sky with nothing but your eyes and your stories. The sun would rise, blaze, set. If it changed subtly, you might never know unless the sky itself responded in spectacle. Ancient civilizations recorded comets, eclipses, strange lights. Chinese court astronomers meticulously documented sunspots as early as 28 BC, noting dark blemishes crossing the solar disk when conditions allowed safe observation through mist or smoke. They did not know about plasma or magnetic shear. They knew only that heaven sometimes marked itself. You imagine yourself standing in a Bronze Age settlement. The air smells of wood smoke and earth. The sun looks slightly hazy through morning fog. If a coherent pulse like tonight's occurred, would anyone notice? Probably not directly. But if it nudged auroras slightly farther south, perhaps a faint red glow would be recorded in a bamboo chronicle or etched into memory as an omen. Mainstream fact. Historical records of unusual auroras have helped modern scientists reconstruct past solar activity. The Carrington Event, for example, was corroborated by reports from around the globe describing brilliant skies. More recently, tree-ring data has revealed sudden spikes in carbon, 14 around 774 to 775 CE and 993 to 994 CE. Events now believed to be linked to extreme solar activity or cosmic radiation bursts. These are called Miyake events, after the researcher who identified them. Historians still argue whether those ancient radiation spikes were caused by massive solar superflares or rare cosmic phenomena like nearby gamma-ray bursts. The debate continues, fueled by isotope data and astrophysical modeling. Tonight's pulse is nowhere near that magnitude. It leaves no isotopic scar in tree rings, no widespread crimson skies chronicled in monasteries. But it invites a softer question. How many subtle solar reorganizations occurred before we had the tools to detect them? You drift through centuries. In 1610, Galileo turns his telescope toward the sun, carefully projecting the image onto paper. He sketches sunspots, challenging the Aristotelian idea of celestial perfection. The sun, once divine and unchanging, reveals itself as dynamic. In 1859, Carrington observes that sudden white light flare. Hours later, telegraph lines spark. Humanity realizes the sun can reach down and touch technology. In the 20th century, radio operators notice mysterious interference. By mid-century, space probes confirm solar wind exists at all. Eugene Parker's theory vindicated. And now, in the 21st century, you measure a star's whisper in nanoteslas and nanometers. There's a quirky historical footnote. In medieval Europe, unusual sky glows were often interpreted as dragons, battles in heaven, or divine warnings. The language was mythic because a framework for plasma physics didn't exist. Today, we replace dragons with magnetic reconnection, celestial battles with coronal loops. The aura remains, the vocabulary evolves. If a coherent solar pulse occurred in 1200 CE and slightly expanded auroral visibility, perhaps a scribe would describe curtains of fire breathing in the north. We would read it now and wonder what solar wind conditions prevailed that year. Historians still argue whether some ancient blood-red skies recorded in chronicles might reflect intense auroral events at lower latitudes, possibly tied to strong geomagnetic storms. But for smaller, structured pulses like this one, the historical footprint would likely be invisible. That invisibility is humbling. It means the sun may have been adjusting itself quietly for millennia, long before humans noticed. Stellar dynamo processes unfolding in cycles, magnetic helicity redistributing, wave packets propagating outward, while empires rose and fell beneath. You picture monks illuminating manuscripts by candlelight, unaware that the star overhead was undergoing subtle magnetic choreography. You picture sailors navigating by stars, trusting a sky whose hidden magnetism was quietly shifting. Tonight, though, you live in an era where even whispers are heard. Global sensor networks span continents. Satellites orbit in layered shells. Data flows instantly between research centers. When the sun exhales in a coordinated pulse, humanity collectively leans in. And yet, the emotional response is different from ancient times. Not fear, not prophecy, curiosity. That shift matters. It reflects centuries of accumulated understanding that the sun is not a temperamental deity, but a magnetized sphere of plasma governed by physical laws. Complex laws, yes, still debated, but laws nonetheless. You feel the continuity of it all. The same fusion reactions that powered ancient harvests power your city lights indirectly through fossilized sunlight stored in fuels. The same magnetic field that guided migratory birds guided ancient mariners' compasses. The same auroras that inspired myths now inspire spectrographs. Historians still argue whether technological society has made us more vulnerable to solar activity than any previous civilization. In some ways, yes, our grids and satellites are sensitive. In other ways, we are more resilient because we understand the risk and monitor it constantly. Tonight proves something subtle. We are attentive enough to notice a gentle stellar recalibration without mistaking it for apocalypse. The sun continues rotating, its far side hidden for now. In 2 weeks, that once active region will begin peaking around the eastern limb again. Researchers will watch carefully, comparing new magnetograms to old ones. You remain here, under a sky that feels ancient and immediate at once. The star above you has always changed. Only recently have you learned how to listen. And as history stretches behind you, inked in chronicles, etched in tree rings, plotted in spectral lines, you realize that tonight's quiet pulse is simply another verse in a very long solar story, one that began billions of years ago, and is still unfolding. Now your mind drifts to the storm everyone always brings up when the sun misbehaves, the Carrington Event. It's the gold standard of solar drama. September 1st, 1859, British astronomer Richard Carrington, calmly sketching sunspots, suddenly observes a brilliant flash of white light erupting from the solar surface. Within hours, astonishingly fast for solar material to travel, Earth's magnetic field convulses. Telegraph systems across Europe and North America spark, fail, and in some cases continue operating briefly even after being disconnected from their batteries, powered purely by geomagnetically induced currents. Mainstream fact: the auroras during the Carrington Event were seen as far south as Cuba and Hawaii. Newspapers described skies so bright you could read at midnight. It remains the most powerful geomagnetic storm in recorded history. Now compare that to tonight. No telegraph sparks, no equatorial auroras, no panicked operators receiving electric shocks while clutching brass keys. The DST index during Carrington is estimated to have plunged below -800 nanoteslas. Tonight's oscillations barely flicker in the single-digit range. And yet, Scientists keep mentioning 1859, not because this event rivals it, but because Carrington reminds us that the sun is capable of both violence and nuance. In fact, Carrington's flare was a classic explosive magnetic reconnection event. Bright, chaotic, energetic. Tonight's pulse appears almost the opposite. Structured, coherent, restrained. Historians still argue whether the Carrington event was truly a once-in-several-centuries anomaly, or if similar superstorms occurred before widespread record-keeping. Ice core nitrate data and tree ring isotopes hint at other intense solar episodes in the distant past. The 774 to 775 CE event, for example, may have been even stronger in terms of radiation influx, though its exact cause remains debated. If Carrington was a shout, tonight was a whisper. But whispers can matter. Modern modeling studies suggest that if a Carrington-scale event struck today, the consequences for power grids and satellites could be severe, possibly trillions of dollars in damage. That's why space weather forecasting has become a serious field, not just an academic curiosity. Governments monitor solar activity daily. Satellites at the L1 Lagrange point provide early warnings roughly 30 to 60 minutes before solar wind disturbances reach Earth. Tonight's pulse triggered no warnings. And that's precisely why it's intriguing, because Carrington-type events are well studied in terms of intensity. We understand the basics of how strong southward magnetic fields, coupled with Earth's magnetosphere, transferring energy explosively. But coherent, low-amplitude pulses challenge a different part of the model. How frequency and structure might influence energy transfer efficiency. It's like comparing a hammer blow to a tuning fork. The hammer delivers brute force. The tuning fork resonates. You imagine if Carrington had possessed today's instrumentation. Spectrographs capturing multi-band radiation in milliseconds. Magnetometers mapping global response in real time. Instead, he had pencil sketches and eyewitness accounts. There's something poetic about that progression. From hand-drawn sunspots to machine learning algorithms combing terabytes of solar data. And here's a curious tidbit. Some researchers have speculated about the possibility of solar superflares, eruptions far stronger than Carrington, based on observations of sun-like stars in distant systems. The Kepler Space Telescope detected superflares on stars similar to ours, releasing up to 10,000 times the energy of typical solar flares. The big question is whether our sun is capable of such an event. Most evidence suggests it's unlikely in its current evolutionary stage, but the debate isn't fully closed. Historians still argue whether isotopic spikes in tree rings represent near superflare events or other cosmic radiation sources. The uncertainty keeps researchers cautious. Tonight's pulse doesn't hint at superflare territory. If anything, it suggests the sun has modes of operation that aren't strictly explosive. Magnetic energy doesn't always accumulate and detonate. Sometimes it redistributes. That redistribution might even reduce the likelihood of larger flares in the short term. If magnetic shear decreased during the event, as earlier data suggests, then some tension was released smoothly rather than catastrophically. In earthquake science, small tremors can relieve stress along faults, but sometimes they foreshadow larger quakes. The analogy isn't perfect. Plasma and rock behave differently, but a conceptual tension between release and buildup remains. You imagine scientists quietly asking, was this pulse a safety valve or a prelude? For now, there's no evidence of imminent escalation. Solar wind conditions remain moderate. The once active region continues rotating toward the far side, its magnetic complexity gradually diminishing in updated magnetograms. The planet remains calm. But Carrington lingers in the collective memory of space weather research like a benchmark of humility, a reminder that the sun is capable of extremes. Tonight's event expands that memory, not upward in intensity, but sideways in understanding. It says, the sun doesn't only shout, it hums. And sometimes, that hum carries across space with surprising clarity. You rest beneath a star that once set telegraph wires on fire, and tonight merely tuned the magnetosphere, like an instrument. Both behaviors are real. Both are part of the same dynamo turning steadily in the core, fusing hydrogen into helium at 15 million degrees, converting 4 million tons of mass into energy every second. The scale is almost absurd. And yet, the difference between catastrophe and curiosity can hinge on magnetic geometry and timing. Carrington showed us the sun's fury. Tonight showed us its finesse. And both remind you that you live beneath a star that is neither entirely tame nor entirely wild, just profoundly, beautifully dynamic. Of course, whenever something unusual happens in the sky, the fringe theories arrive right on schedule. You can almost hear them warming up. Some corners of the internet begin whispering about solar upgrades and encoded light frequencies, A few dramatic posts claim the sun has shifted into a new vibrational state. It's poetic language, less plasma physics, more cosmic self-help seminar. And while it's tempting to roll your eyes, it's also deeply human. For thousands of years, unexplained sky events have invited storytelling. Mainstream science, meanwhile, stays grounded. The data shows a coherent, multi-band emission event linked to magnetic shear reduction in a coronal loop. It shows resonance in Earth's magnetosphere. It shows symmetrical rise and decay patterns. None of that implies intention, messaging, or mystical transformation. Plasma doesn't have a personality. It follows Maxwell's equations. Still, the fringe isn't entirely devoid of interesting questions. There's a long-standing minority hypothesis in astrophysics that stellar magnetic systems may occasionally enter globally synchronized states, not mystical, just physically coherent. Similar to how certain chaotic systems can spontaneously self-organize. It's not widely accepted as a dominant behavior, but nonlinear systems are full of surprises. Plasma turbulence can produce emergent structures. Solar cycles sometimes show double peaks or asymmetries not fully predicted by dynamo models. Historians still argue whether the Maunder minimum, a period from about 1645 to 1715 when sunspots became exceedingly rare, reflects a temporary shift in the sun's dynamo behavior or simply a modulation within expected variability. During that time, parts of Europe experienced colder winters, though the connection between solar activity and climate remains complex and debated. The idea that the sun can enter unusual modes isn't fringe at all. The question is scale. Tonight's post doesn't suggest a grand transformation of the solar cycle. It suggests a localized, coherent magnetic adjustment. Subtle, measurable, contained. But fringe interpretations often leap from subtle to seismic. You smile gently at the pattern. Humans dislike ambiguity. When something new appears, we either minimize it, just a glitch, or inflate it. Cosmic awakening. The truth usually lives somewhere quieter in between. There's also a curious scientific fringe worth mentioning. Some plasma physicists have explored whether stars might exhibit behaviors analogous to phase transitions, like water freezing into ice, under certain magnetic conditions. It's highly theoretical. The sun is far too hot and dynamic for little phase changes of that sort, but magnetic topology can reorganize in ways that resemble shifts between ordered and disordered states. If that language sounds dramatic, remember, even chaos theory grew from once fringe mathematical exploration. Still, extraordinary claims require extraordinary evidence. Tonight's data shows no runaway amplification, no escalating instability, no cascading flare sequences. The coronal region involved appears to have stabilized after its magnetic adjustment. No dragons, no galactic Wi-Fi password updates. There is, however, a fascinating scientific edge case worth pondering: resonance amplification. In complex systems, resonance can sometimes produce effects disproportionate to input energy. A small periodic force, applied at just the right frequency, can produce large oscillations. Engineers design bridges carefully because resonance can turn steady winds into destructive vibrations. The famous Tacoma-Narrows Bridge collapse in 1940 is a classic example. Wind-driven oscillations matched the bridge's natural frequency, leading to dramatic failure. Historians still argue whether similar resonance principles could amplify certain solar, magnetospheric interactions more than our current models predict. Tonight's event is too weak to cause damage, but it hints that frequency content matters as much as amplitude. That's not mystical. It's mechanical. Meanwhile, the sun continues its quiet rotation. The active region responsible for the pulse has diminished in magnetic complexity. Helioseismic farside imaging shows no unusually large emerging regions poised to rotate into view. Solar wind conditions remain within expected parameters for this phase of the cycle. The fringe may imagine cosmic transitions, but the evidence suggests something more modest and more interesting: a star briefly demonstrating a coherent magnetic mode that we hadn't clearly categorized before. You lie there beneath it all, perhaps amused by how quickly narratives form around incomplete information. It's a reminder that science thrives on patience, on replication, on cautious interpretation. The researchers involved will publish carefully worded conclusions, consistent with suggestive of further study required. No sweeping proclamations. And that's reassuring, because while the universe is vast and sometimes violent, it's also governed by principles that can be tested, refined, understood. The sun didn't awaken into a higher dimension. It adjusted its magnetic scaffolding, and that adjustment traveled across space as a coherent pulse that brushed your planet without harm. Sometimes the most extraordinary explanation is simply better measurement, and that's a far more powerful story than any dramatic headline. Even within mainstream science, debates simmer long after the data settles. You imagine conference halls months from now, rows of astrophysicists half listening while scrolling through slides dense with spectra and magnetograms. A presenter advances to a graph showing that familiar symmetrical spike. Laser pointer circles the peak. We propose this represents a coherent magnetic relaxation, event distinct from classical flare morphology. A hand rises in the back. Could this simply be an under-resolved subflare with atypical decay parameters? And just like that, the polite duel begins. Historians still argue whether many so-called new solar phenomena are genuinely new or merely newly resolved by better instruments. When high-resolution telescopes came online, granulation patterns on the sun suddenly looked more complex, not because the sun changed, but because our vision sharpened. The same happened when X-ray monitoring became continuous. Previously unseen microflares appeared everywhere. So the core question lingers. Did the sun behave differently, or did we finally notice something it's always done? You drift through the logic. On one side, researchers emphasize the multi-instrument confirmation, coronal loop brightening, magnetic shear reduction, synchronized radiation bands, magnetospheric resonance. The probability of all those aligning by chance seems low. On the other side, skeptics caution against overfitting patterns. With enough datasets, small correlations will emerge. Statistical rigor demands restraint. It's a healthy tension. Mainstream fact, scientific consensus often forms slowly through replication and independent confirmation. The discovery of gravitational waves, for instance, required multiple detections before acceptance solidified. Even then, debates about interpretation continue in specialized corners. Solar physics is no different. Some teams begin combing archival data more aggressively, looking for historical events with similar frequency coherence. Early machine learning results suggest a handful of candidates over the past 2 solar cycles. Weak, previously overlooked events exhibiting partial symmetry. If confirmed, that would imply tonight's pulse is not unique, just rare and subtle. Historians still argue whether rare solar behaviors cluster around solar maximum due to heightened magnetic complexity, or whether they occur randomly throughout the cycle but become more noticeable when monitoring intensity increases. There's also renewed scrutiny of the solar dynamo model itself. The sun's internal magnetic engine remains only partially understood. We know convection and rotation generate magnetic fields. We know the 11-year cycle reflects polarity reversals. But predicting exact timing and structure of active regions remains challenging. Some models incorporate meridional flows, plasma circulating from equator to poles and back again, while others emphasize turbulent diffusion. If coherent relaxation events are real, they might represent an intermediate mechanism for magnetic energy redistribution within the cycle. That possibility excites theorists. You imagine equations being adjusted late at night, boundary conditions tweaked, simulations run with slightly altered magnetic diffusivity values. Supercomputers hum quietly, modeling plasma loops tens of thousands of kilometers long. And then there's Earth's side of the debate. Space weather specialists wonder whether forecasting models should incorporate spectral analysis of incoming solar radiation beyond intensity alone. If frequency matching enhances magnetospheric coupling, predictive algorithms might need to track not just strength, but structure. It's subtle progress, the kind that rarely makes headlines but quietly improves resilience. Meanwhile, critics caution that the event's amplitude was too small to justify sweeping model changes. Interesting, they'll say, but not transformative. Perhaps they're right. You reflect on how knowledge often expands, not through revolutions but through refinements. Newton didn't overthrow Aristotle in a single afternoon. Maxwell didn't unify electromagnetism without decades of incremental understanding. Even Einstein built upon foundations laid before him. Tonight's pulse may simply become another data point, small but precise. Still, there's something satisfying about witnessing science in motion. Not the dramatic breakthrough montage, but the slow, methodical sorting of possibilities, the humility of uncertainty. Historians still argue whether the pace of modern scientific discovery has accelerated beyond our capacity to absorb it, or whether it simply feels faster, because information spreads instantly. In truth, most discoveries still require patience. The sun rotates on, indifferent to debates. The once active region has nearly slipped beyond view now, dissolving into quieter, magnetic patterns. If it produces another coherent pulse when it rotates back, skeptics will have less ground to stand on. If not, the event may remain a fascinating outlier. Either way, the archive grows richer. You lie beneath layers of atmosphere, magnetism, and accumulated knowledge. Above you, plasma Bayes equations were still refining. Below you, researchers argue gently over interpretations. And that, perhaps, is the most comforting part. The universe doesn't need to be fully understood to be safe. It only needs to be studied carefully. Tonight's pulse has become less of a mystery and more of a conversation, between data and doubt, between theory and observation, and the conversation continues. While debates ripple through conference rooms, another shield quietly holds its ground, the one wrapped invisibly around your entire planet. You drift outward again, past the ionosphere, beyond low Earth orbit, into the vast cavity carved into space by Earth's magnetic field. The magnetosphere stretches tens of thousands of kilometers toward the sun and trails millions of kilometers behind in a long magnetic tail. It is sculpted continuously by the solar wind, compressed on the day side, elongated on the night side. Mainstream fact: Earth's magnetosphere is generated by convection currents in the liquid outer core, where molten iron moves due to heat escaping from the inner core. This geodynamo has been operating for at least 3.5 billion years. Without it, solar wind particles would gradually erode the atmosphere, as appears to have happened on Mars after it lost its global magnetic field. Tonight, that magnetosphere was tested, but gently. When the coherent solar pulse arrived, magnetometers detected small oscillations propagating along field lines. These were not violent compressions like those seen during major geomagnetic storms. Instead, they resembled standing waves, energy moving through the system without overwhelming it. Imagine plucking a taut string. The string vibrates, but it doesn't snap. Field line resonances occur when incoming energy matches the natural oscillation frequency of magnetic field lines, loaded with plasma mass. Each string has its own pitch, determined by magnetic strength and plasma density along its length. Tonight's pulse matched one of those pitches closely enough to set it humming. Historians still argue whether resonance effects play a larger role in space weather dynamics than previously appreciated. Traditional models often emphasize bulk solar wind pressure and magnetic orientation, but frequency-specific coupling could represent a subtler layer of interaction, one that doesn't require brute force. You float along a magnetic field line in imagination, arcing from the northern hemisphere into space, and back down toward the southern hemisphere. Charged particles spiral along this path, guided by Lorentz forces, bouncing between mirror points near the poles. During the pulse, their motions subtly synchronized. Satellites in the magnetotail detect faint compressional waves traveling downtail, reflecting off boundary layers and dissipating gradually. No reconnection substorms ignite. No dramatic plasmoid ejections hurtle into space. The system flexes, then settles. There's something profoundly reassuring about that resilience. Earth's magnetosphere has endured billions of years of solar variability. It has withstood stronger storms than this by orders of magnitude. Paleomagnetic records show that Earth's magnetic field has even reversed polarity many times, north becoming south and vice versa, without stripping the atmosphere or extinguishing life. Those reversals take thousands of years, and during them the magnetic field weakens. Yet fossil records show no corresponding mass extinction directly linked to reversals. Life persists. Tonight's oscillation is microscopic by comparison. Still, scientists are curious about one detail. The efficiency of energy transfer during the pulse seems slightly higher than expected for such a modest solar wind amplitude. Modeling suggests that resonance may have amplified magnetospheric response more effectively than standard pressure-driven coupling would predict. If that's true, forecasting tools might one day include resonance probability indices, calculations of how incoming solar frequency spectra align with magnetospheric eigenfrequencies. It sounds esoteric. It could improve prediction accuracy. There's also renewed attention on how magnetospheric waves interact with radiation belts, zones of energetic particles trapped by Earth's magnetic field, also known as the Van Allen belts. These belts can swell during geomagnetic storms, posing hazards to satellites. During tonight's event, radiation belt monitors show only slight modulation in particle flux, again synchronized, again small. No dramatic injections of high-energy electrons, just a gentle ripple through an already dynamic system. You sense the scale of it all. The magnetosphere is not a rigid shell. It breathes. It oscillates. It reconnects and reforms constantly. It's less a shield wall and more a dynamic membrane, responding to solar input in complex ways. Historians still argue whether early Earth's magnetosphere was stronger or weaker than today's, and how that influenced atmospheric retention and radiation shielding. Some evidence suggests the young sun was more active, producing stronger winds. If so, Earth's magnetic field may have been crucial in preserving oceans and enabling life. Tonight, that ancient dynamo performed flawlessly again. The pulse arrived. The field hummed. Energy dissipated harmlessly. You lie on the surface of a planet protected by molten metal spinning 3,000 kilometers beneath your feet. It's an astonishing arrangement when you think about it, and yet it feels normal. The oscillations dampen fully now. The magnetotail relaxes. Field lines return to baseline curvature. The planet's magnetic heartbeat steadies. The sun continues shining, indifferent. But for a brief window, star and planet were linked by a frequency match, a shared tempo across empty space. And the shield held, as it always has. By morning, the graphs look ordinary again. You imagine researchers scrolling back to the previous day's data, watching the spike appear and disappear and fast forward. Without context, it's just a blip. With context, it's a conversation between star and planet. Now the question shifts from what happened to what it means. Mainstream fact. The sun is currently moving through solar cycle 25, which began in December 2019. Early predictions suggested it might be relatively mild, similar to the previous cycle. But updated observations show it's slightly stronger than expected, with higher sunspot numbers and more frequent flares. Solar forecasting is notoriously difficult. Cycle amplitude predictions often miss the mark. So where does a coherent magnetic pulse fit into that bigger rhythm? Some researchers propose that as solar maximum approaches, magnetic complexity increases not only in intensity, but in structural diversity. In other words, we might expect not just more flares, but more varied magnetic behaviors. Tonight's event could represent one such variation, a non-explosive redistribution of magnetic energy during peak dynamo stress. Historians still argue whether solar cycles exhibit subtle secondary patterns, quasi-biennial oscillations layered atop the 11-year rhythm. Data hints at periodicities around 2 years in certain solar indices. If coherent pulses correlate with these subcycles, they might become predictable. Predictable is a dream. Imagine space weather models that don't just say flare likely, but coherent relaxation event probable within 48 hours. It sounds niche, but understanding frequency-structured emissions could refine everything from satellite shielding protocols to radiation exposure forecasting for astronauts. Speaking of astronauts, low Earth orbit crews aboard space stations experience increased radiation during strong solar events. Tonight's pulse posed no measurable hazard. Dosimeters remain steady. But as humanity eyes deeper space, Artemis missions to the moon, eventual voyages to Mars, understanding subtle solar variability becomes increasingly important. Outside Earth's magnetosphere, shielding is thinner. If coherent pulses are part of the sun's magnetic vocabulary, mission planners will want to recognize them, even if only to confirm they're harmless. There's also a philosophical layer to all this. For centuries, humanity feared sudden celestial change. Comets meant doom. Eclipses meant omens. Now, when the sun behaves unexpectedly, we gather more data. That shift from superstition to spectroscopy is extraordinary, and yet humility remains necessary. Historians still argue whether our current models of stellar dynamos will look quaint in 100 years. Just as early atomic models seem simplistic now, today's solar simulations may eventually appear incomplete. Each new observation is both a step forward and a reminder of limits. Tonight's pulse expands a parameter space slightly. It says, the sun can release magnetic tension coherently, without flare chaos, and Earth can respond resonantly without storm-level disturbance. That's not apocalyptic. It's nuanced. The once active region has now rotated fully out of Earth's view. Helioseismic farside imaging shows it fragmenting into smaller magnetic patches. If it reemerges 2 weeks from now and produces another coherent pulse, confirmation will strengthen the case for a defined category. If it doesn't, the event remains a rare gem in the data archive. Either outcome enriches understanding. You imagine a future solar physics textbook, including a short section titled Coherent Magnetic Relaxation Events. Perhaps it cites this very pulse as one of the earliest well-documented examples. Perhaps it doesn't. Science is selective in what becomes canonical. Meanwhile, the sun continues its relentless fusion, converting hydrogen into helium, radiating energy in all directions equally. Every second, about 3.8 times 10 superscript 2 watts pour outward. Earth intercepts a tiny fraction, just enough to power weather systems, photosynthesis, and your next sunrise. Against that staggering output, tonight's pulse is minuscule, and yet it mattered because it revealed structure within apparent chaos. It hinted that magnetic systems can shift gracefully, not only violently. You rest beneath a star that is neither static nor unpredictable beyond comprehension. It is dynamic within bounds, creative within constraints of physics. Tomorrow, the sky will look the same. Weather forecasts will mention clouds, not coronal loops. Most people will never know that a coherent magnetic wave crossed interplanetary space and tuned the magnetosphere like an instrument. But you know, and that knowledge carries a quiet wonder. The sun is not just a furnace. It is a living laboratory of plasma, magnetism, and resonance. And tonight, it showed you a new trick. And now you return to where you began, standing beneath an ordinary sky. The sun rises again, bright and unapologetic, as if nothing subtle or scientific happened at all. Birds argue in trees. Traffic hums. Coffee machines hiss like tiny domesticated steam engines. Above you, 150 million kilometers away, a sphere of plasma continues fusing hydrogen into helium at 15 million degrees in its core, unaware of your curiosity. Mainstream fact. The photons warming your face this morning began their journey in the sun's core thousands to tens of thousands of years ago. They bounce randomly through dense plasma in a process called radiative diffusion before finally escaping the surface. Then once free, they cross space in 8 minutes. The light you see now carries a history far older than your entire civilization. Somewhere inside that immense engine, magnetic fields are already twisting again. Differential rotation continues, shearing them. Convection cells churn. The dynamo hums. The sun does not pause because you notice one coherent pulse. Historians still argue whether humanity's increasing technological sensitivity to solar variability marks a fragile era or a resilient one. On one hand, satellites, power grids, and communication networks create vulnerability. On the other, our monitoring capability has never been stronger. We watch the sun continuously. We model its moods. We prepare. Tonight's event, quiet, structured, resonant, reminds you that relationship with a star is not binary. It is not only calm or catastrophe. It is spectrum, texture, nuance. You imagine the magnetosphere again, flexing like a breathing lung of invisible force. You imagine auroral arcs brightening in gentle rhythm. You imagine radio waves bending ever so slightly through a temporarily thickened ionosphere. All of it synchronized for a handful of minutes because magnetic frequencies align just right. Not a threat, not a miracle, just physics expressing itself elegantly across distance. There's something grounding about that. For all the dramatic headlines humanity gravitates toward, the universe often operates in subtle adjustments. Magnetic shear reduces instead of snapping. Energy redistributes instead of detonating. Systems resonate instead of collapse. You stand on a planet with molten iron core generating a magnetic shield. You orbit a star capable of both fury and finesse. You exist in a solar system buffered by a heliosphere stretching billions of kilometers into interstellar space. It's an astonishing configuration, and yet it feels normal. That may be the greatest comfort of all. Cosmic processes can unfold at unimaginable scales without destabilizing the fragile routines of daily life. The sun can hum in a new way, and you can still wake up, stretch, and check the weather. The coherent pulse is already archived now, stored in data centers, plotted in academic papers, debated in seminars. Over time, it will become less mysterious. Models will incorporate it. Students will learn about it as an example of magnetic relaxation or resonance coupling. Or perhaps it will remain an outlier, rare, curious, a footnote reminding researchers to keep listening carefully. Either way, it has already done something valuable. It has reminded you that understanding is a process, that vigilance does not require fear, that the star at the center of your sky is dynamic without being malicious. You breathe in slowly. The air is still here because Earth's magnetosphere has held for billions of years. The oceans remain because solar wind has not stripped them away. Life persists because layers of atmosphere absorb radiation long before it reaches you. Tonight's pulse tested none of that in any serious way. It simply tuned the system gently. And perhaps that is a quiet lesson. The universe does not always announce change with catastrophe. Sometimes it experiments softly, adjusting magnetic scaffolding in ways only careful instruments detect. You are living in an era capable of detecting those whispers. That is extraordinary. The sun will continue turning. Solar cycle 25 will crest and eventually decline. Another cycle will follow. Magnetic poles will flip again, as they have for centuries. Somewhere in the future, perhaps a stronger pulse will come, or another coherent one, cleaner and more defined. When it does, humanity will be watching. For now, the sky above you is blue by day, star-studded by night. The magnetosphere rests in equilibrium. Satellites glide in silent arcs. Power grids hum. Signals travel cleanly. And the star that once set telegraph wires sparking has shown that it can also speak in measured tones. You are safe beneath it. You are curious beneath it. And you are part of the first generation capable of hearing its faintest magnetic music. The sun shines on, steady and magnificent, and you drift gently under its light, knowing that even when it changes in ways we've never seen before, the story it tells is one of physics, patience, and quiet resilience. Now let the pace soften. The data has been logged. The graphs have flattened. The auroras have dimmed back toward the poles, folding like curtains at the end of the show. Earth's magnetic field returns to its baseline murmur, a steady, invisible presence you rarely think about. Imagine the planet from far above, a blue sphere turning slowly in darkness, wrapped in a faint magnetic cocoon. Solar wind flows around it like water around a stone in a stream. The sun glows at a safe distance, immense but constant. Nothing urgent is happening now. The pulse has passed. The resonance has faded. Systems have settled. You can let your thoughts slow, too. Picture the sun not as a threat, but as a distant hearth, vast, controlled by gravity and fusion, radiating warmth across the void. Every sunrise you've ever seen came from that same engine. Every leaf that ever grew, every breath of oxygen you've taken, traces back to its light. Tonight, it whispered in magnetism. Tomorrow, it will rise again, ordinary and bright. You are held between star and core, fusion above, molten iron below, balanced in a narrow band of safety carved out by physics over billions of years. There's comfort in that stability. No alarms, no storms, just a dynamic universe, continuing its quiet work. Let your breathing match that steady rhythm. Inhale, as Earth's magnetosphere flexes gently in the solar wind. Exhale, as the oscillations dampen into calm. The sun shines. The planet turns. You rest beneath both.